we start to speak about this, fix this again. Let's fix once and for all some measure space where mu is an arbitrary measure. So mu of the total S is a number between 0 and infinity, including infinity. And then let's recall, let's then start to work with this space of simple non-negative measurable functions. And our definition is that we define the integral of f with respect to measure mu as a sum of some values ai, and then we weight them by some measures ai. And here we denote the range of f by, so the range of f is the set of possible values of f, and that is denoted now by these numbers a1 up to am. And this ai is then the pre-image. So ai is the pre-image of the value little ai. Here is the definition. Does it make sense? Let's see. We have a summing something. F has a finite range. It's here, and then we look at the pre-images. So okay, we want to calculate the measure of each capital AI. Can we do it? Are these measurable sets? Note that this is a singleton set. Singleton set is a Borel set. So we are looking at the pre-image of a Borel set. So then that means that because we assume the f is measurable, so then the pre-image of every Borel set is not in B, but those pre-images are now in the calligraphic S. So that's why we can calculate the measure of each of these sets AI. These could be finite or infinite. These are finite and non-negative. So let's point out that all of these values are non-negative because f was assumed to be a non-negative function. And so that's why this value of the sum is a number between 0 and infinity, including infinity. And it is well defined as such an extended number. Alternatively, we can also write this as the sum of values x in the range of f. And we write here x times the measure of the pre-image of this singleton set f. This way. So, and maybe if you like, you could also write this informally as the sum of x times the mu of the set where f takes the value x. So we could write it as the mu of f equals x. Yep. And maybe a note. Let's do a little example of an alternative notation. So assume now that we are looking at the probability space, and now we have a probability measure. And then if we think about x being a now simple function from omega to the real line and non-negative, and we use this definition, so then what would now be the integral of x against this probability measure p? So note that this is now in the same setting as here, and then we could write it as the sum of x in the range of the capital X, x times the probability measure of the set pre-image of the capital X of little x. So we could write it as probability big X is the small x. So what you see on the right is what is actually used in the basic course in probability and statistics as the definition of the expectation of a random variable x. Yep. So this example kind of illustrates that what we are looking here when we plug in mu as a probability measure. So then this integral corresponds to this type of expectation of a random variable x.